So let's talk about the shape of logarithmic functions in general. So if we have f of x is equal to log base a of x, where the base a is greater than 1. Okay. Now remember, for logarithmic functions, the base a has to be greater than 0, not equal. So we're just looking at the case where the base is strictly greater than 1. Okay. So the general graph for a logarithmic function with a base greater than 1 looks like this. Okay. Remember, we did this for exponential functions. Okay. And so it crosses the x-axis, right, at the point 1, 0, where x equals 1. Okay. So that's the general shape of a logarithmic function when the base is greater than 1. Okay. And so its domain is x has to be greater than 0, which is the set of all positive numbers. Okay. So this tells me right away, right, that you can't take the log of 0 or a negative number. That's important to remember. You can't take the log of 0 or a negative number. Okay? Let me write it this way. The range well, there's no minimum y value, right, because the graph goes down forever. And it actually goes up and to the right forever, but at a very slow pace. And so the range is all real numbers. The x-intercept, right, crosses the x-axis at x equals 1. So the x-intercept's x equals 1 or the point 1, 0. And then lastly, the vertical asymptote, right, the y-axis, which coincides with the vertical line x equals 0, is the vertical asymptote. Remember, vertical asymptotes are vertical lines. Any questions? So now we're going to draw what the log function looks like in general when a is between 0 and 1. Okay? And it has the same characteristics, same domain, range, x-intercept, and vertical asymptote. What's different is the shape of the graph. So we have f of x is equal to log base a of x when the base is between 0 and 1. And when the base is between 0 and 1, instead of the graph going up from left to right, it goes down from left to right. So you basically just take this graph and flip it over the x-axis. Same domain, same range, same x-intercept, same vertical asymptote. Any questions? Well, just as we had a very special exponential function called the natural exponential function, we have a very special logarithmic function called the natural logarithmic function. Okay. So the natural logarithmic function, okay, is the inverse function of the natural exponential function. Okay. So the natural exponential function is y equals e to the x, if you recall. So here's the graph of y equals e to the x. Crosses the y-axis at y equals 1. Okay. The natural exponential function, okay, then looks like this. Remember, an exponential function is inverse function, right? Are reflections of each other across the diagonal line y equals x. Well, because the natural exponential function is a special function, it gets its own special notation. Okay. So f of x, the natural logarithmic function, is the logarithmic function in base e. Okay. Remember, e is that special number equal to 2.718. So f of x equals log base e of x is the natural exponential function. And because it's a special function, it gets its own special notation. And it gets the notation ln. So whenever you see ln, that's replacing log base e. Okay. All right. So natural exponential function, it's its own special notation. And so this on the right here, phonetically is pronounced Ln of x. I often say natural log of x instead of ln of x, right? But it's the same thing. Now, about the natural log function. Okay. You know, on the left here we have f of x. F is the name of the function, and x is the input to the function. Okay. With the natural log, right? The natural log function, right, is just a special function with a special name. So we can write ln of x with x in parentheses. Okay. Just like we put the x in parentheses in f of x. When we're using letters of the alphabet like this for the names of a function, we always put the input in parentheses, okay? With the natural log function, we sometimes drop the parentheses, right? We can put the input with or without parentheses around it. So this notation and this notation are the same thing, okay? Sometimes we include the parentheses, we put the input in parentheses, and sometimes we don't. In both cases, okay, X is the input. So ln is a special name for a special function, okay? And X is still the input. But sometimes we drop the parentheses, okay? It's optional. Parentheses are optional. And a lot of times it clarifies things if you do put the input in parentheses. Okay. All right. So this is the graph of the natural exponential function, and this is the graph of its inverse, the natural log function. Okay. And then the inverse of the natural log function is the natural exponential function, right? They're inverse functions of each other. Okay. All right. So some properties of the natural logarithm. Are the following. Logarithm. The natural log of 1 the log, you know, so I'm doing both, right? I'm including parentheses and without to indicate, right? You can put the input in parentheses, or you can leave off the parentheses. The log of 1 in any base is equal to what? 0. Right? So we did the properties of log base A. Okay. And so we're doing the same thing. Okay, only it's log base C now. Okay. The natural log of e to the first power is just equal to 1. Okay. This is e to the first power, and the natural log function and the natural exponential function are inverse functions of each other. And they basically undo each other, and so we're just left with the exponent 1. The natural log of e to the x is just the exponent x. So here was the exponent 1. Here the exponent is x, so the natural log of e to the x is just equal to the exponent x. And then we have e raised to the natural log of x is just equal to x. And again, the natural log function and the natural exponential functions are inverse functions of each other, so they undo each other, and you're just left with the exponent x here, and here you're just left with the input to the natural log function x. So those are 4 very important properties of the natural log function. Any questions on that, ladies and gentlemen? Okay. All right, let's talk about laws of logarithms. And you know how there are laws of exponents that we reviewed back in section 5.1? There were like 6 of them. There are laws of logarithms, but there are only 3. Okay. So these apply for any base a greater than 0 and not equal to 1. Remember, the base has to be a positive number not equal to 1. Okay. and positive numbers, m and n. And this will also apply to variables like x, y, and z. Okay. So the first rule is called the product rule. And it says the log base A of m times n is equal to, anybody remember what it was from high school? It's the, right, so you're taking the log of a product. So it's the log of the first number plus the log of the second number. And then you go the other way as well, right? The log of m plus the log of n is equal to the log of m times n, right? You can switch the two sides of the equal sign. And now in terms of the natural log, we have the natural log of m times n is the natural log of m plus the natural log of n. So remember, the natural log function, you just replace this log base A with ln, right? It just gets its own fancy notation. The quotient rule, log base A of the fraction m over n. Well, instead of adding two logs, you subtract them. It's equal to the log of the numerator minus the log of the denominator. So in terms of the natural log, we just replace log base A with ln. We have the natural log of m over n is equal to the natural log of m minus the natural log of n. So it's a product quotient. And now lastly, we have what is called the power rule. And we have the log base A of m raised to the c power. Okay? So this is m raised to the c power. You maybe remember from high school what we can do with this c? Bring it down in front of the log. So this is equal to c times the log base A of m. And then with the natural log, we have the natural log of m to the c power is equal to c times the natural log of m. Okay. And c in this case is any real number.
It's not like a subscript or an exponent anymore, the c.
The c is an exponent on the number n.
But like after, it's big.
Here?
Yeah.
Yeah, c
Okay.
times.
So it's a big number.
Yeah. So this is the natural m raised to the c power. This is the real number c times the natural log of m. Okay, it's a product on the right hand side. So let's demonstrate these properties. first one is the natural log of 1 over e. Okay. Well, this is a fraction, right? And quotient rule applies to fractions, right? So by the quotient rule, this is equal to the natural log of the numerator minus the natural log of the denominator. Well, the natural log of 1, right? The log of 1 in any base is 0. And we erased it, but one of the properties of the natural log was the natural log of e to the first power is just equal to 1. So natural log of 1 minus the natural log of e is equal to 0 minus 1, which is equal to just minus 1. Any questions on that, ladies and gentlemen? Okay. Next we have the natural log of the square root of e. Well, you know, square root is the same as raising something to the 1/2 power. So this is equal to the natural log of e to the 1/2 power. And from the properties of the natural log, we've already erased. The natural log of e to the x, remember, we have the natural log of e to the x is just x, right? So our x in this case is just 1/2. And so the natural log of e to the 1/2 is 1/2. Next we have e raised to the minus 1/2 times the natural log of 16. Well, we have the property of the natural log function that e raised to the natural log of x is equal to x, right? But we don't have e raised to the natural log. We have e raised to the minus 1/2 times the natural log. But the power rule says if I have c times the natural log of m, I can bring this c inside the natural log and make it an exponent on the number m, right? When I switch the two sides. So I can take this minus 1/2, bring it inside the natural log, and make it an exponent on the number 16, okay, from down here. So just to switch the two sides, c times the natural log of m is equal to the natural log of m to the c power, right? All I did was switch the two sides of the equal sign. So this minus 1/2 can be brought inside the natural log and made an exponent on the number 16. So the exponent on the number e is minus 1/2 times the natural log of 16. And now I'm going to take this minus 1/2 and make an exponent on the number 16 inside the natural log. And I have e raised to the natural log of 16 raised to the minus 1/2 power. So you got to be careful. Now I got two exponents. Minus 1/2 is an exponent on the number 16, and the natural log of 16 to the minus 1/2 is the exponent on the number e. Are you with me? Okay. Well, over here, okay, e to the natural log of x is just x, right? So our x in this case is 16 to the minus 1/2 power. So the natural exponential function and natural log function cancel each other, and we're just left with 16 to the minus 1/2 power, right? That's our x from over here. Well, the minus sign in the exponent means reciprocal, so this is equal to 1 over 16 to the 1/2. Right? This is from the rules of exponents. And anything raised to the 1/2 power means square root. So this is equal to 1 over the square root of 16, and the square root of 16 is 4. So e raised to the minus 1/2 times the natural log of 16 simplifies to 1/4. Any questions on that, ladies and gentlemen? It's at the end of the semester where you remember at the beginning of the semester we talked about you got to study 2 hours for every hour of lecture. At the end of the semester, that's where that really comes into play. Last half of the semester. All right. Now we're going to simplify log base 2 of 6 minus log base 2 of 15 plus log base 2 of 20. So you notice they all have the same base, all three logs have the same base. We're dealing with real numbers. So that all equals a real number. Okay. We're going to figure out what it is. All right. Now, we have a difference and a sum, right? So, just to review the associative property of addition and subtraction, okay? You know that 5 minus 3 plus 7, I can switch the order of subtraction and addition and write that as 5 plus 7 minus 3, okay? Same quantity. So I'm going to put the plus log 20 in front of the minus log 15. And I have log base 2 of 6 plus log base 2 of 20 minus log base 2 of 15. I'm just doing to make the math easier for me. Okay. Box that so we don't confuse it. So the product rule says the log of one number plus the log of another number is equal to the log of the product of those two numbers, right? We go from the right side to the left side. So the log of 6 plus the log of 20 is equal to the log of 6 times 20, okay, by the product rule. So this is the log of 6 times 20, okay? And now I'm using parentheses just to clarify, okay? That the input to this log function is this product, 6 times 20. Okay. Are you having a hard time seeing?
No, I can see.
Okay. And then we have minus log base 2 of 15. Now remember, these are all the same base, right? So I can use, right, the laws of logarithms. Can you see below this one?
No.
So don't go any lower.
Okay.
Is that what you're saying? Okay. Well, quotient rule says the log of a number minus the log of another number is equal to the log of the first number over the second number, right? I can write this difference as a log of a fraction. So 6 times 20 is our first number, 15 is our second number, right? So I can write that as log base 2 of the first number, 6 times 20, over the second number, 15. Okay. Now I could have wrote 6 times 20 is 120. Okay. If I left it as a product. And now you know the input to this log is 6 times 20 over 15, which is equal to 8. So this is equal to log base 2 of 8. Does anybody know what log base 2 of 8 is equal to? What is it? Yeah, it's 3. Now, one of the properties of logarithms we can use from the other day is 8 is equal to 2 cubed. And log base 2 of 2 cubed is just equal to 3. Right? You have those properties. Now, an alternative way, okay, is to set log, here's an alternative way of solving that. Log base 2 of 8, we'll set that equal to y, right? And this exponential, remember there's y equals log base a of x, and x equals a to the y are equivalent equations, right? So we can go from a logarithmic equation to an exponential equation. Right? The x in this case is 8, the base a is 2, and the exponent is the unknown y. And now you can solve this for y. 2 raised to what power is equal to 8? 3, right? 8 is equal to 2 cubed. 2 cubed is equal to 2y. And by the one-to-one property of exponentials, we have y has to equal 3. So there are 2 different ways of doing this, okay? Of figuring out what log base 2 of 8 is equal to. Alrighty. So we are at the end of the period, okay? There's only a minute to spare. And so we'll wrap this up on Wednesday before we take our quiz, okay? So have a good day, and I'll see you on Wednesday.